The Hall effect, as explained by Kcee and Allie. The Hall effect was discovered by Edwin Hall in 1879. It describes how a difference in voltage is produced across a conductor.
So let's first assume that we have a conductor connected with two electric cables and battery. And we let the current flow through this conductor in the right direction. Then we have a magnetic field added to the sides. So in this case, if we use a voltmeter to measure the top side and the bottom side of this conductor, we'll see a number, and that number would be the voltage difference of this conductor. Now let's take a look at the concept of the Hall effect.
There are many freely moving charge carriers within the conductor. These negatively charged carriers move in the direction opposite to the electric current I. By using the left-hand rule, we find that the velocity is towards the left, and the magnetic field is pointing forward, which leaves the Lorentz force, which is a magnetic force, pointing upward. However, because the carriers are negatively charged, the magnetic force is pointing downward instead. The downward force drags the carriers towards the bottom left. Thus, the negative charges accumulate on the bottom of the conductor, leaving the positive charges on top of the conductor. Now, we have most of the negative charges on one side of the conductor, so it has a negative and a positive side. This phenomenon happens because as we have a magnetic force pointing downward, we also have an upward electric force acting on the charges. This electric force cancels the magnetic force on the moving charges. The magnetic force then produces a charge separation which builds up until it is balanced by the electric force. An equilibrium is reached instantaneously, producing a measurable voltage between the two sides of the conductor. In the other case, if we have positively charged carriers flowing in the conductor, these carriers are moving in the same direction, right, as the electric current I. Using the left-hand rule, the Lorentz force will be pointing downward. The downward force tends to drag the carriers to the bottom left direction. Thus, the moving positive charges accumulate in the bottom of the conductor, leaving the negative charges on the top of the conductor. One application of the Hall effect is to identify different semiconductors. N-type. The bottom surface is negatively charged and the upper surface is positively charged. The Hall voltage produced by the N-type semiconductor is negative. P-type. The bottom surface is positively charged and the upper surface is negatively charged. The Hall voltage produced by the P-type semiconductor is positive.
By using this formula below, UH is equal to RH times IB divided by lowercase b, where UH is the voltage, RH is the Hall constant, I is the current, B is the magnetic field, lowercase b is the width of the conductor. We're able to calculate the magnetic field. This formula will also help us to understand better about the anti-lock braking system, which is another application of the Hall effect.
The anti-lock braking system is widely used on land vehicles such as cars, trains, and buses. It functions using the Hall effect. Hall effect ABS sensor. A magnet is placed on the left of the Hall effect sensor, and a toothed wheel is placed on the right of the sensor. As the wheel is rotating, if one of the small metal strips, the teeth, is facing the sensor, the magnet will magnetize the metal strip, and the magnetic field of the center of this sensor will become very strong. Using the formula, we know that the strong magnetic field would result in a high voltage. As the wheel is rotating, if none of the teeth are facing the sensor, the magnet will magnetize the two consecutive metal strips and disperse the magnetic fields, which leaves the center of the sensor with a weak magnetic field. Using the formula, we know that weak magnetic field would result in a low voltage. A Hall effect sensor senses the voltage change as the wheel is rotating, and it can calculate the time between two high voltages. Also, the angle change of the metal strips can be measured since two metal strips pass the center of the sensor when two high voltages occur. With the change in time and change in angle, we can calculate the angular velocity is equal to dt over d theta. The ABS sensor uses this wheel rotation speed to prevent the wheel from locking up when braking. Thank you for watching our video. I hope this helped you better understand the Hall effect and all of its applications.